Welcome to our analysis of xenon tetrabromide by Varsan and Ishraq. To start to understand our molecule, we're going to use our most basic form to view our molecule, the Lewis dot diagram. To do that, first we will start with our central atom, which in this case is xenon. Now we know that our molecule is going to have non-octet bonding because any molecule with a noble gas's central atom automatically bonds non-octet, meaning it doesn't need 8 valence electrons. It doesn't want to fill up a shell when it creates its bonding. As a result, what we're going to do is we're going to arrange our bromine atoms around it. So we have 4 bromine atoms, we're going to put them like a plus sign, up, down, left, right, and we're going to link it with single bonds connecting each bromine to the central atom xenon. However, this is not our Lewis dot diagram. We need to do some more calculations. So let's start the number of electrons we have. We look at it and we find that xenon has 8 electrons because it's a full noble gas, and bromine each has 7, 7 is 28, so we get a sum of 36. Now, we're going to subtract our 8 because each bond has 2 electrons. Now, let's fill out our surrounding bromine atom, 6 for each. And that takes up 24 of our electrons, leaving us with 4. 28 minus 24 is 4. So we're going to put down the 4 as 2 lone pairs. Each lone pair has 2 electrons. But we want to go dive a bit further than our simple Lewis dot diagram. So some bonds and our valence electrons. In fact, we want to see our molecule in 3D. So if you notice around here, we have the total of 1, 2, 3, 4, 5, 6. We have 6 electron pairs. Therefore, we can say that the geometry of our molecule, xenon tetrabromide, is classified as an octahedral. Having this said, we can now proceed to do our Weissenberg theory, waves electron to reversion theory. So we have 6 electron pairs, so the geometry is going to be octahedral. So this is our central atom. So in this molecule, say we have our central atom, there's 2 electrons on top, 2 electrons at the bottom. They're on polar opposite sides. And then the square is formed around the equatorial. And in each of this, there's a bromine. In fact, you could notice that the equatorial, the 4 bromines, they make a square. And the angle formed between these of actually 90 degrees, the right angles. So, therefore, our angle is 90 degrees. And as a result, we know that therefore, the shape of our molecule is a square planar. Of course, the 4 bromines make a square with the electrons lone pairs on the top and the bottom of xenon at polar ends in the square in the middle, square planar. But now let's talk a bit more about this molecule. When you already visualize 3D as per the valential electron pair repulsion theory, let's take a look at, say, how it bonds. What we're going to talk about, we're coming to here, is let's start for making an electron configuration for our central atom, xenon. I'm still keeping the Lewis dot diagram as a frame of reference. We'll be using it throughout. But xenon is actually on the 5th row. It is the last one. It's in the P6. It's the end of that row. So the electron configuration for xenon is, if you look at the periodic table, 4, D, 10, 5, P6. That's the row. And at the start, we have krypton. It's krypton 5s2, 4d10, 5p6. And after having this as our electron configuration, let's make an energy level diagram for our atom. Now let's draw our shorthand energy level diagram. So we're going to draw our y-axis, which is our potential energy. We're going to draw this in black. And we're going to also draw out our x-axis. So first of all, we're going to separate our s, p, and d orbitals. Each of these have to get their own section in an energy level diagram because they all represent different types of orbitals. So we're going to separate them with dotted lines. And then first we're going to write out our noble gas that comes before it. After we have that, what we're going to do is we're going to check it out. We have a 5s orbital. So we're going to set up our 5s orbital, label it, and then we're going to set up our 4d orbital, label it, and finally we're going to set up our 5p orbital. All of these are in the same color as black, but now we need to do our electrons. We're going to use a red color for our electrons to show it. So according to Aufbau's principle, electrons fit up in energy levels like lowest to highest. So that's the order we're going to follow. And according to Hund's rule, each orbital would get one electron before the other would pair up for like each section, like 5. So first we're going to draw out up and down as per Pauli's exclusion principle due to the spin. We're going to do 1, 1, 1, 1, 1, fill it all up. And now that we have filled it all up, we're going to do the other way, down, 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 down. We have draw 10 electrons, we have 6 more in our 5p, which we are going to fill up 1, 2, 3, 4, 5, and 6. Now having our shorthand energy level diagram, we can now do our hybridization. Our hybridization occurs because we don't have just xenon, we have xenon tetrabromide, so there are bonds for which we need to consider. So first we're going to label our hybridization by showing an arrow to show the change in the central atom's energy diagram. First we need to identify the bonds so we can reference the Lewis dot diagram. We have labeled 6 of our electron pairs. We have 1, 2, 3, 4 sigma bonds. These are sigma bonds because bromine has 7 electrons around it, so it only needs 1 electron to bond. The one comes from the central atom xenon. We also have 2 lone pairs, which we have identified in our green marker. So we write it down as 4 sigma bonds along with our 2 lone pairs. Having done this, we can now proceed to draw our hybridization diagram because we already have it in that. So we draw out our axes again. Now we need to draw, but we need to draw the hybrid orbitals in the middle of the 5s and the 5p, since 5 is the outermost energy level numerically. Not 4, it's 5. So in the middle, we draw out our 6 orbitals because we have 4 pi bonds and 2 lone pairs. 4 plus 2 is equal to 6. So first let's draw out our pi bonds, and each pi bond there is 1 electron with upward spin, which we label. And now we have our 2 lone pairs left. So we're going to have to label those two with 2 electrons in each, so since they are full. So this is our hybrid orbitals, but now we need to label it. And to label it, first we get our number, which is 5. And we have 6 orbitals, so let's do 1 for S. And having done 1 for S, there's 3 for P. And then we have 2 left, and that comes from a d orbital. So we have 2 in d. So we have 5 sp3 d2. This is our hybrid orbital name. So we have went from our shorthand energy level consists of the central atom to an shorthand energy level diagram of our central atom. Using that and identifying our bonds, we are able to draw the hybridization of our atom.
Already drawn earlier, let's redraw the Lewis dot diagram for xenon tetrabromide. Let's take a deeper look into the molecule and find the intramolecular forces present. So in order to determine our intramolecular forces, we need to find the electronegativity difference. We need to find the electronegativity of xenon and bromine. So let's take a look into our periodic table. Bromine has an electronegativity of 2.8, while xenon has an electronegativity of 2.6. So let's write those down, 2.8 and 2.6, and now we will find the difference between these two. And when we subtract them, we can see that the electronegativity difference is 0.2. Since our electronegativity difference is 0.2, it's less than 0.4, which is the threshold between being a pure covalent and a polar covalent bond. In this case, since it's less than 0.4, it's actually a pure covalent bond. So let's go ahead and highlight the pure covalent bonds that are present in our Lewis dot diagram. This also means that each bond between xenon and bromine is nonpolar because both atoms share electrons equally, with neither being slightly positive or slightly negative to each other. In this diagram, you can see that xenon and bromine are bonded to each other with 2 electrons in the middle that are being shared. This other diagram is showing that xenon and bromine are both attracting it the same amount, with neither attracting it more than the other, and this is because their electronegativities are very close to each other. Let's analyze whether there are any special bonds like coordinate covalent bonds or resonance structures present. So are there any coordinate covalent bonds? How do we figure this out? Well, we look at the surrounding atoms. Let's go ahead and count how many electrons are in the surrounding atoms and then look at the group that it's in. So we have 1, 2, 3, 4, 5, 6, and 7 electrons in the surrounding atom bromine. So each of the bromines has 7 valence electrons. However, this isn't a problem because it's actually in group 17, the halogens, which means it's supposed to have 7 valence electrons. Since that number 7 isn't exceeded, then each bond is actually a sigma bond, not a coordinate covalent bond. In that case, let's go ahead and label each bond as a sigma bond. Let's check for any resonance structures that are present in this molecule. Are there any? There's actually none, and the reason is because they're all sigma bonds as we just labeled, meaning there's no pi bonds or double bonds that can create a resonance structure. Therefore, we have no resonance structures. To find our properties, let's determine if xenon tetrabromide is polar or nonpolar. We already established that every single bond in xenon tetrabromide is identical, and earlier we also determined that they're all pure covalent or nonpolar bonds. We already know that in the central atom xenon, there's 2 lone pairs, so let's highlight those lone pairs in blue. Our next objective is to determine molecular symmetry. Drawing 2 lines of symmetry going down and across, we can see that it's symmetrical on both sides of the lines. This means that the entire molecule is symmetrical, and combining all of these facts, we now know that xenon tetrabromide is a nonpolar molecule. And because xenon tetrabromide is a nonpolar molecule, the only intermolecular force that acts on it is London dispersion force. Let's do a quick valence count of xenon tetrabromide and H2O to really grasp their sizes. So xenon has 54 electrons. Let's write that down, and 4 bromines are present, and each bromine has 35 electrons. So 4 times 35. Adding those two values up, we get a total valence count of 194 electrons in xenon tetrabromide. And what about the valence count for H2O? We have 2 hydrogens present with each having 1 valence electron and 1 oxygen with 8 electrons. When adding those 2 up, we get 10 valence electrons in total in H2O. Seeing these two numbers up close really shows how big xenon tetrabromide is. Subtracting them, we can see that xenon tetrabromide has 184 electrons more than an H2O molecule. It's a fact that xenon tetrabromide is a ginormous molecule, as we just counted the number of electrons that are located within it. The large size and the large number of electrons means that there's increased LDF forces between xenon tetrabromide and other molecules. It also means there's a higher possibility of temporary dipoles forming, thus increasing attraction between xenon tetrabromide and other molecules. Here there are two xenon tetrabromide molecules that are being attracted to each other through LDF, or London dispersion forces. The large size of xenon tetrabromide means that the valence electrons are very far away from the nuclei, so the attraction holding them is weaker and thus can experience temporary dipoles much easier with other molecules. This can also be termed as being more polarizable. We can further prove that xenon tetrabromide is a solid because when we look at the halogens, and we go down the group of fluorine, chlorine, bromine, and iodine, we see that it goes from gas to liquid to solid. The general pattern that we see is that as electrons increase, then LDF increases, and altogether in xenon tetrabromide, these London dispersion forces add up, and we can predict that because these attractions are so strong, it's actually very likely to be a solid. Now, to do a brief summary of the intermolecular forces in xenon tetrabromide and H2O, we know that xenon tetrabromide has LDF, but it's huge. Water, on the other hand, has hydrogen bonds, dipole-dipole, and LDF. Again, we know that LDF is considered weaker than hydrogen bonds and dipole-dipole, but considering the size of xenon tetrabromide, it's actually the stronger force as it's all combined together compared to the weaker hydrogen bonds, dipole-dipole, and LDF of H2O. Therefore, we can conclude that xenon tetrabromide is a solid at room temperature, mainly because the intermolecular force of the combined LDF is stronger than those present in H2O. Since covalent compound solids are frequently flexible and soft, we predict that xenon tetrabromide to be a soft covalent compound. However, this would require analyzing its lattice structure to confirm whether it's true or not. Being a solid at room temperature and predicted to have stronger intermolecular forces than water means that this molecule has a higher melting point than water. And this is mainly because it would require more energy in order to break apart the stronger forces in xenon tetrabromide as opposed to H2O. Thus, we can conclude that xenon tetrabromide has a higher melting point than water.